Hey guys, so this is the kickoff to our next unit in Tech and Engineering, Electricity and Circuits. This will kind of segue into eventually programming and coding and working with Arduino. This may be a review for some of you. I think Electricity and Circuits was part of the sixth grade science curriculum, but that was a while ago. So I just wanted to make sure that we all have a base knowledge moving forward so that we can kind of freely talk about some of these terms with everyone kind of knowing what's going on. So this is part one, just the basics, and as we kind of move forward throughout the weeks, we'll be introducing some new content. So within this unit, we'll be answering a few essential questions. One, what is electricity? How do we define electricity? We all know electricity is all around us. We use it every day, but let's put a definition to it. Number two, what are the components of electricity? How do these components affect electric circuits? And lastly, number three, how is electricity measured? So put simply, electricity is the flow of electrons through a conductor. We'll be talking a lot about electrons throughout this unit. A lot of the electrons and some of this content you will kind of dive into more deeply in chem sophomore year. So if you've already taken chem, you should know this stuff already. If you're taking it next year, just know that you'll kind of take a deeper dive into atoms and things like that when you do get into chem. So during electricity, free electrons jump from atom to atom, being driven along from the negative side, where there's a very high concentration of free electrons, to the positive side, where there's a low concentration of free electrons. So the negative side of any conductor or any power source always has a high concentration of free electrons. That's why it's generally negative. And those electrons kind of want to move to the positive side and get away from that mass of electrons where there's a low concentration of free electrons. And we say that electrons flow from an area of negative charge to an area of positive charge. We can also compare electricity to diffusion. We can also call it the diffusion of electrons. You see here in this little animation, these blue kind of slashes are electrons moving through a circuit. This is the symbol for a battery. We'll get into electrical symbols in a few lessons, but this is a symbol for a battery, starting from the negative side of the battery, moving through the conductor, lighting the light bulb, moving around the circuit to the switch, and back to the positive side of that battery. Other examples of diffusion, first one, smells diffuse or move throughout your home. You always know when chocolate chip cookies are baking in the oven. Even though that smell is concentrated in the kitchen where the chocolate chip cookies are being baked, it'll slowly move throughout your home, and you'll know if you're up in your room, those chocolate chip cookies are coming out of the oven. Also, heat dissipates through things can be like another way to compare diffusion of electrons to something in real life. We can't talk about electricity without talking about conductors and insulators. Again, this may be a review, but just so we're all on the same page. Conductors are materials with low resistance, allowing for the flow of current. And insulators are materials with high resistance, forbidding the flow of current. Common examples of conductors: tinfoil, lemons. Believe it or not, a lot of citrus fruits are good conductors as they have a high concentration of free electrons. A screwdriver, just because it's made out of metal. Copper is probably the most common example of a conductor. A lot of wires are made out of copper. And then lastly, salt water, which I'll talk a little bit more about in a second. And then we have insulators: cardboard, plastic, rubber, glass, oil, and wood. You'll notice if your computer's plugged in right now or you have an extension cord in your room, on every kind of wire throughout your house, it'll be coated in some sort of rubber or plastic material, and within that rubber or plastic material usually is copper. So even though there's a conductor within that wire, it has an insulator wrapped around it, so that current or that transfer of electrons doesn't come to you, come into your body when you touch that wire. So why is salt water considered a conductor? Salt molecules are made of sodium ions and chlorine ions. If you haven't taken chem already, what is an ion? An ion is an atom that has an electric charge because it has either gained or lost an electron. Again, you'll get into ions a little bit more when you do take chem. When you put salt in water, the water molecules pull the sodium and chlorine ions apart, so they are floating freely. So essentially, you just have a bunch of free floating electrons within that salt water solution. And these ions are what carries electricity through water. So I took a little clip of a video from YouTube, kind of just showing you how this person was able to light a light bulb using salt water as part of the circuit. So they start with just kind of a container of water. There are alligator wires attached to two nails here. Salt is going in the water. Take a look at the light bulb. Almost instantaneously, that light bulb lights. So this is a power source back here. You can trace the flow of electrons from the power source to the lamp, through the wire. It goes through the saltwater solution, back up through the nail, through the wire, and back to the power source. As he mixes the salt into the water, you'll notice that the light bulb gets a little bit brighter. So if we were in class, we could do this together. I wouldn't suggest you try this at home, but just know that this can be done. So electricity is measured in two ways. The first way is through current, and the second way is voltage. So current is the measure of the rate at which electricity is flowing. So how fast electrons are moving through a circuit or moving through a conductor. The symbol for current is I. I know it kind of seems weird because current starts with a C. A lot of times symbols are representative of the word or term itself. But the symbol for current is I, and the unit for current is amps. 1 amp is when 1 coulomb, or 6.25 times 10 to the 18 electrons, so that's millions and billions and trillions of electrons moving past a point in 1 second. So how fast those electrons are moving past 1 point just in 1 second. How do amps affect us? It's kind of hard to, see amps, but 1/1000th of an amp you can feel. 1/100th of an amp can paralyze muscles, paralyze temporarily, or if it's kind of flowing through you for too long a time, it can actually paralyze it permanently. And then 1/10th of an amp can be fatal if it lasts for a second or more. So just thinking about that, not even 1 amp can kill you. Be careful, the outlets in your homes are rated 15 amps. So there's so much power coming from your outlets at home. And we just said that 1/10th of an amp can be fatal. And we have 15 amps coming from our outlets at home. So that's always when you were younger, your parents probably plugged up your outlets with those little outlet covers just because they didn't want your little baby hands getting in those outlets because it could be fatal. So we can calculate current by dividing charge in motion, which is symbolized by the letter Q in coulombs, divided by time per seconds. We are never going to have to calculate current. That's something you may do in physics, but just know that this is the equation that you can look to calculate current. So I is electric current in amps, Q is the charge in motion, which is coulombs, and T is time in seconds. So which carries more current, thick wires or thin wires? Definitely thick wires. Why? There's more conductors in a thick wire. You see there's hundreds of strips of copper within these thick wires and only a few in these thinner wires. So the more conductors, the more copper you have within a wire, the more free electrons that can move throughout that conductor. So we said that in the beginning of this presentation, we said that electrons flow from negative to positive in a circuit. So electrons flow from negative to positive, but current flows opposite. Current is flowing from the positive side of a circuit to the negative side of the circuit. You always kind of want to remember that this is opposite, especially once we get into calculating current and drawing some of these schematic diagrams in the future. So, like I also said, we can also measure electricity within a circuit through voltage. So voltage is the potential difference or electrical pressure between 2 points, or the difference in charge between 2 points. The symbol for voltage is V, easy to remember. And the unit is volts, so voltage, volts. In my opinion, this is the easiest one to remember. Everything's pretty similar. So voltage is the force that causes electrons to move in a common direction along a conductor. So it's a force. So it's what's pushing those electrons through a conductor. What are some ways voltage can be created? The first one is chemically, like within a battery. If we were in class, we would be doing some kind of experiments and creating some circuits during a lab using just batteries. It's the easiest kind of form of voltage or power that we can get our hands on. Also light. Some of you may have solar panels on the tops of your house, kind of supplementing some of your voltage power within your home. Heat can also create voltage. Physical pressure. Magnetism. I don't know if any of you have ever used one of those little DC motors, but there's actually a magnet within there that's kind of spinning copper kind of around the part of the DC motor, which kind of creates that voltage or creates some sort of power. And then last but not least, friction. So like rubbing your shoes on a carpet. So we can calculate voltage by dividing work by charge. So we've already seen Q in the previous equation for current. So in this equation, voltage is symbolized by V, and that's in volts. W is work or potential energy in joules. And then Q is charge, which is in the unit coulombs. So again, we'll never have to calculate voltage itself and kind of break it down into this simplest form. You may do this when you get to physics junior year, but it's just nice to know kind of where this voltage rating is coming from. We also talked a little bit about resistance when we talked about conductors and insulators, so it's important that we kind of define resistance as well. Resistance is the opposition to the flow of electrons, a material's tendency to resist the flow of charge or current. The symbol for resistance is R, so that's easy to remember. And the unit for resistance is ohms, and this is the symbol for ohms. It's actually a Greek letter. So which has a greater resistance, conductors or insulators? Hopefully, you'll all know that insulators have a greater resistance. So again, some more examples are rubber, ceramic, plastic, wood, air, and glass. These all resist the flow of electrons, but items like metals, concrete, dirty water, like we just talked about, salt water, or graphite, are conductors. So those have a lower resistance to the flow of electrons, so electrons can easily flow through those. Resistance of a wire depends on several factors. The first one is the material itself. There are certain metals that are better conductors than others. Like we said, copper is probably the most common. The length of that wire, longer wires have greater resistance, shorter wires have less resistance. There's kind of less material that the electrons have to flow through. Thickness of wires, and then also the temperature of a wire will affect resistance. So I think this cartoon kind of does a nice job of showing the relationship between resistance, current, and voltage. So you can see here that the volt is kind of pushing the current, which is measured in amps, through the wire. So the voltage is the force, the current is what's flowing through the wire, and then you see the ohm on the top here kind of resisting current from flowing through a wire. So if you ever get confused, I think this is a perfect kind of image to look at. And then also, just this little diagram here shows, so this is a wire. If we take a cross-sectional kind of snapshot of that wire and zoom in, you'll see all the electrons flowing through the wire. So that's basically current, like we've been talking about. So we talked about three components of electricity. A very common analogy to kind of explain electricity is called a waterfall analogy. So you obviously in a waterfall have water, which is the substance that's flowing. You have the waterfall itself, which is gravity, which pushes the water down the waterfall. And then you have rocks. Those could be the obstructing force. You may have rocks below the waterfall. You may have rocks throughout the waterfall, or branches or trees or anything like that. So in this example, current can be compared to the water, okay? Current is what's flowing. That's the substance that's flowing. Voltage is the pushing force within a circuit. So that's the waterfall itself, or gravity. That's what's pulling the water down. And then lastly, we can compare rocks to resistance within a circuit. That's what's obstructing the water from flowing down. It may slow down the water from flowing, things like that.